This is going to be like a pachuchichu, a little bit. A pechacucha. I can never remember how to say that. Yeah, it was all moving before. Okay, let's see. Okay, there we are. So we're going to start with the basics of physics, right? How heat moves from hot to cold, moisture moves from wet to dry, warm air rises, like the stack effect, and air pressure moves from high to low. These things don't care what your religion is, your political background, whether you wear, have blue hair or not. They do what they do, and they don't care what your intention is. They will just act. So we're going to talk about water. Water has amazing three forms, and it takes energy for it to phase between these forms. It's ice, solid, water, a liquid, and a gas. All right. Of course, these phases have change and have a relationship to temperature at the bottom and to pressure. But we kind of live in this zone with our buildings, little tiny sliver of how that reacts. So we're going to start with that freeze thaw, that change from a solid to a liquid. When it's a solid, the molecules are bound together in a very orderly manner, and they're kind of expanded. And when it melts, they more fall into more of a random pattern. So when that's inside a material expanding and contracting, right, that's that freeze thaw cycle that is very dangerous. And different materials react differently to that freeze thaw type cycle. And this is just an example of two main things: sheathing. So the bottom is plywood and the top is OSB. And you can see that the OSB is much more sensitive to water. So that freeze thaw is going to have a lot more impact on an OSB product than a plywood. And every product has whatever their profile is and how they react to different things. And of course, OSB, if you haven't flashed it properly, if you have air leaks and so moisture is getting into that, you don't protect it properly, you have a disaster on your hands. Like these disasters, where air leaks, lack of flashing, reverse flashing, all kinds of things, improper weather barriers, etc., cause disasters. So atmospheric pressure, right? I don't know if you did this when you were in elementary school, the test where you take the cup of water and you put a piece of paper on. That's atmospheric pressure that is greater than the pressure of the water, and it keeps that water from falling out. So we have defied gravity here. And that surface tension is another one of those kind of wonderful, magical things that happen with water. And adhesion and cohesion, that's how it attaches to other objects and how it attaches to each other, water molecules. So they beat up on things, etc. And so, we have things called a drip edge, right? That drip edge is to get that water to drip off the edge of things rather than sort of gathering and pulling itself back up into the wall. And so if you don't have a drip edge, you have disasters like this, right? This is why I hate fiberglass roofs when they're also used as coping. There's no drip edge here, and it is completely sucked up and rotted out this substrate, right? So the other thing is a kerf, right, which interrupts this water wants to suck into this wall, and this is a way to keep that water and get it to behave the way physics is gonna, you work with physics, you say, okay, what is physics? And so the size of that little space matters, right? That water will suck up more and faster in a little tiny space than a bigger space, which is why the code now, since 2015, identifies a drainage plan as being really important, and that it has to be at least 3/16 of an inch, right? That little bit of space. If you, and I would always go, the code is minimum, it's 20 years old, it's minimum, and try to go beyond code. So the other thing is capillary action, which is related to surface tension and that cohesion. And it's like a sponge, this is a brick, and this is a brick at 5 minutes, 18 minutes, 64 minutes. and you're seeing that it's sitting in water, and it's a reservoir system like stucco is. You know, these actually take on water. We know they do, which is why we have drainage planes and an airspace behind a brick wall. So that's also why we have this thing called rising damp, right? When we underpinned our basement here, we put a layer before, at the last little layer of that footing, was a water impermeable non-shrinking grout, right? That helps stop that rising damp. Rising damp can go 20, 30 feet into the air, up a wall. It's just amazing how it will defy gravity. You've probably seen this diagram, water vapor. So now we've phase changed that water and it's become vapor. It needs some kind of warmth, and warmth and pressure and stuff will increase that. And it wants to suck into your building. Now it can go through different kinds of materials, but if you have a hole, it goes through much faster. This is why air barrier is so important. Because air is bigger than vapor. So you can stop the air, but the air will also carry vapor. But vapor can move through a smart air barrier so things can dry out. This is a improperly neither vented nor unvented pilot house ceiling. And because it really wasn't vented, but they put insulation in there, we get mold and mildew, right? You have to have, if you do unvented, you have to have 3 inches of air impermeable insulation touching that sheathing, and all insulation has to touch each other without any gaps or things. And what does mold love? Mold loves moisture. If it has some food to eat and it has the right temperature and you have moisture, you're going to get mold, right? So condensation, that's when that vapor now is phasing back into liquid, right? So if you have a roof drain is going down through your building, you better insulate it, because it's going to condensate inside that ceiling and you're going to have a mess. And then just that air barrier, right? This is, you know, underneath this was an improperly, it was neither a vented or an unvented condition. And this air was coming up through systems, hitting this. You see there's no, this architect did not draw a water barrier, weather barrier underneath this cap. And it wasn't put on there, and it just rotted all to hell. Then there's those little air spaces, or not so little. So this is trying to do an unvented roof. They've spray foamed this. It's not very regular. It's not 3 inches consistent. So you're going to get condensation in places, and this insulation is not touching that. So you get a convection loop, which really moves that warm air and creates a little, you know, petri dish in here, right? And then we see things like this, right? This jigsaw puzzle, and here's this big gap where they were trying to do an unvented condition, but they didn't strap that insulation up against it. And this is another part of that same roof where, you know, what a crazy, you know, jigsaw puzzle is that. And then this is our right? This is a steel beam under a sliding door. And of course, there's no air barrier, there's no insulation. So it's just a little condensation place where water gathers and it rots everything out. So think all of this, all these physical things work holistically within a building. So you can't just, you know, single something out. You have to think of it together. So let's get our act together and do it right, because buildings don't get touched again for at least a quarter century or more. And so we bake these things in, and it's just my way I end my slides. That's it. That's my little building science moment. Screen 2. Okay, that's it. Okay. Can you see me now?
Yes, we can see that now.
Okay, so